Okay, ladies, so today we're learning about moving into our real second type of inference testing, which is tests for significance. Okay, ladies, so let's get into introduction to hypothesis testing. So the goal of a significance test, which is what we're going to be talking about with hypothesis testing, is to assess evidence provided by data about some claim concerning a population. So basically, someone is making a claim about the population, and we're going to be using data to assess, is that claim accurate, is it not? So the first thing that you need to know with your claim is essentially what's the parameter of interest that we're talking about. And for me, the best way I can think about this is doing a simulation with you. So the parameter of interest that we're going to look at is the proportion of free throws a player will make if she shoots forever. So the way you would see this in real life is you have a player that claims, I make free throws 80% of the time. Really? Is that true? Okay, so there's our parameter, the proportion of free throws that she'll make if she shoots forever. And we would write that as our tested claim is the proportion is going to be 0.8. So now we've got a lovely little applet down here that you can check out, and we're going to go do a simulation. Okay, ladies, so here's what we're doing. This was, again, the claim that somebody shoots 80% of the time they make their free throws. So let's go ahead and hit shoot. Some misses there, some hits. Okay, and right here is showing what the claim was at 80%. This is getting closer to 80, but it's not quite there. So here we have hits 64% here, and misses 36%. So that's kind of a interesting way of doing this. Not quite 80, right? Well, let's shoot some more just to be on the safe side. Maybe we just need to shoot more often. Not looking like it's approaching 80. Okay, so as I get closer and closer, I'm not necessarily convinced that this claim is true. I'm going to show the true probability here, but before I do that, if you'll notice, it's probably a lot lower than 80%, right? So here's our true probability. Yeah, 60%, not at all 80. Okay, let's get a new shooter. Okay, and we're going to hit this one more time, same deal. Let's see what this one does. The shooter, whoa, 100% of the time for a while there. That was a lucky streak. Okay, then we're going back down below a little bit. Okay, so this time we had 60%. We're going to shoot again. Okay, again, I'm not necessarily sure that it's going to come to that claim of 80 there, but this is starting to approach it a little bit more. Now it's going away. I might just hit shoot one more time to see if I can get just that many more baskets in there, to see if with more data it will approach the population mean a little bit more accurately. Alright, well, it's tending to go to that line. So in this case, it's pretty close to my population. It might be accurate. Let's look at the true. The true is 80. So again, this data was a lot more accurate for this. Notice that it was wildly fluctuating and then slowly, got closer to our true proportion. Okay, so back to our information. So our tested claim was probability of success with free throws was 80%. For the first player, not true. Second player, true. So how did we figure out, was our claim accurate? How did we test our claim? Well, essentially, we did a simulation. We did many repeated trials, and we said, was it accurate? So let's say she would have made 10 out of 25 shots. So that gives us a p-hat of 0.4 here. If that's the case, if that was what our data said, there is strong evidence to say that our proportion is nowhere near 80%, so not 80%, if that was our data. But then the question arises, well, what if you get something like a p-hat of 0.76? Is that strong enough evidence to say that it's not 80? So this is what hypothesis testing is really all about. Okay, so essentially what we're doing here is we are taking a statistical test, and the statistical test weighs the evidence against a claim. Now this is very important, against a claim. So we're not trying to prove that something's true, essentially we're trying to prove that it's not. So we make some claim like you can shoot a free throw at 80% of the time, and our job is to prove that you can't, essentially is what we're doing. So how do we do this? We do it step by step. First we start with the hypothesis, and this is a truth that we want to ascertain, a claim that's being made. And then we make some statement about, a very specific statement about the parameter that I'll talk about a little bit later, like that this parameter is this. Then what we do is we express the results of a significance test in terms of a probability that measures really how well the data and the claim agree. And then essentially what that does for us is we have a claim about the population, we have data, and what a significant test is, the whole point of that is to ask ourselves, does this give good evidence? Does our data give good evidence that this claim is in fact true? So another way of saying that is, if we took many random samples and the claims were true, we would rarely get a result like XYZ. So in order to get a numerical measure of how strong the sample evidence is, we're going to use some probability. Okay, ladies, let's take a look at our example. Let's think about it. So let's say we have a shooter who makes 32 out of 50 free throws. So that's, pretty good. So what's the p-hat for that? Well, let's see. We have 32 that were made out of 50 total. So that gives us a p-hat of, using my handy dandy calculator, 0.64. So 64% of the time this person is making it from the data. So now I'm going to ask, okay, well, what would happen if we ran many, many samples of 50 free throws? What kind of data would we get? And how likely is it that we could get a p-value, or the p-hat, sorry, with a value of p that was actually 0.8. So let's take a look at this here. Okay, so this is a Fathom data set, and it's a picture here of 400 sets of 50 free throws. So each shot represents the proportion of made shots in one set of 50 attempts. Essentially, you can say how strong the evidence is against the player's claim by giving the probability that she would make as few as 32 out of 50 free throws if she really makes 80% in the long run. So if we look at our data right here, we're going to see that in 400 sets, there were only 3 times, those 3 little dots, it's beautifully circled right there for you, only 3 times when our shooter made as few as that observed 0.64 probability if, in fact, the true population was 0.8. So what's the math on that? 3 out of 400? That would be a probability of 0.0075. It's very unlikely that if I'm observing a 64% of her getting her free throws, that it is actually 80 that she's claiming. So the claim doesn't have a lot of legitimacy in my mind. So let's go through how we would actually do this. There's essentially two explanations for why you would see this data. Point one, the claim is correct. The true probability is in fact 80% or 0.8, but by some weird random bad luck, a very unlikely outcome occurred. Okay, or two, the population proportion is actually less than 0.8, so the sample result is not likely to occur, or rather is unlikely in the case of a true proportion of 0.8. So explanation one could be correct, but it would be by chance alone. So such a result would occur by such a small chance that we're pretty confident that number two is right. This lady is lying about the amount of free throws that she actually hits. Okay, ladies, so using our previous example, statistical tests use elaborate vocabulary, and an outcome that would rarely happen, like the outcome that we got, if a claim were in fact true, is good evidence that that claim is not true. So the fact that we got in our data that she hit 64% of her baskets likely means that the claim is not true. So how do we state this in statistical terms? Well, we begin with a statement of the claims that we want to compare. So we start with something that's called a null hypothesis, or H0, and this is the statement of no difference from what was claimed. So this is essentially what was claimed. So for ours, it was what was our null hypothesis, and there's a very specific way to write it. So we would write H sub 0, colon there, and then we would use our parameter, and we would say we were claiming that, or the original claim is that she hit the baskets 80% of the time, 0.80 proportion. Okay, so that's our null hypothesis. This is the claim that that is being made. There's also something called the alternate hypothesis, or H sub A. This is what we hope or suspect to be true instead of the null hypothesis. Okay, and in this particular case, what would our alternate hypothesis be? Well, we don't have a specific number, but we were doubting her abilities. So we would say, okay, I think it's going to be less than 0.80. Okay, so we have our null hypothesis, we have our alternate hypothesis, and then we need to define P. So we'd say P equals our long run proportion of made free throws. And anytime you start a problem, you would state the null, you would state the alternate, and you would define your parameter. Okay, so in our last example, the alternate hypothesis was one-sided because we were interested only in whether the player is overstating her free throws. So we didn't care if she was above 80 or below 80%. We were assuming that she was below 80. So that's the test that we did. But that doesn't have to always be the case. You can, in fact, sometimes you want to find an alternate hypothesis that is simply different than the one that is stated. So in that case, I might say like so this would be an example of two-sided. I may be making a claim that someone is making a claim that the mean is 0. But in fact, I'm not sure, so the alternate hypothesis is the mean is not 0. That way it could be the mean could be higher than 0 or lower than 0. just not 0. So that's another example of, again, our null and our alternate hypothesis. This would be two-sided, the one we just did one-sided. Okay, now like the good scientist you are, you know that you do not state a hypothesis before you see the data. In fact, the hypotheses, you come up with your question, someone makes this claim, the hypothesis is pretty much the first thing you're doing. You're stating what the claim is, your null, and you're stating what you think is really more accurate for the claim. And that would be your alternate hypothesis. So it's really important that you make sure that hypothesis comes first. You can't cheat and look at the data and then come up with your hypothesis. So here's basically the form that this kind of takes. Your null hypothesis is a parameter and it equals a value, and this is always, always, always true. It always gets this equal sign because somebody is making a claim. This is 80%, this is 70%. So our null is always a actual value and set to an equals. Now we have different scenarios for our alternate hypothesis. Sometimes we have a parameter and we think alternately that the parameter is actually larger than the value that was given. Okay? Or we might think that the alternate hypothesis is the parameter is less than the value that was stated. Or we could say that the parameter is not equal to the value, remembering that this goes above and below the value. So this is kind of the two-tiered test. So it's key to remember too that the hypothesis is in terms, don't write the hypothesis in terms of sample statistics. It is always, 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 always in terms of the parameters. So you're referring to the population, not the sample. So make sure that you're talking about it in terms of parameters. And that's it.